I'm a research fellow at the Alan Turing Institute affiliated with Warwick University. So as many of you know, and as many of you are interested in applying machine learning to new areas, I think it's exciting now that machine learning AI is now starting to make very life-changing decisions, from anywhere from things like predictive policing to advertising to insurance to lending to whatever you want to do. But we should be a bit cautious in this pursuit because we've started to notice as a field, as researchers, and the public started to notice that there are significant problems with current methods when we throw them out into the real world, like face detection, not being able to see the faces of black people, advertisements that are biased against individuals with traditionally African American names, in that they'll show advertisements related that say, has this person been arrested? And for example, this is LaTanya Sweeney, who's a Harvard professor of government, Googling herself, and we see results asking if she's been arrested. Things like natural language processing systems that make sexist associations. So let me go into more about what these examples look like and propose a solution. First, by just describing an example of law school admissions. So let's imagine you're in law school, and you have this sort of data about current law school students. So you have, their gender, their race, their undergraduate GPA before law school, their law school entrance exam. This is the U.S. Law school entrance test, and then their current law school grade. And you want to use machine learning to make a predictor from these things to the last thing, how well they're going to do in their first year of law school. Now immediately, we might be concerned about using these two things, because if we do in our classifier, then we're going to make different decisions by definition if people have different values of these quantities. So one natural idea is to just remove these and try to make a predictor with the remaining features. But there's a big issue, and many of you are familiar with this, that these sensitive attributes sort of pollute the unsensitive attributes. For instance, students of a certain race may find that teachers are unsupportive of them, or on the other hand, teachers may believe that students, they may be biased against these sort of students. They think they might have behavior issues. So the problem here is that the features if we try to use in a machine learning algorithm are biased. Even if we try to do something a bit more clever by making sure that we're equally accurate for different, let's say, races, we may also find that the label itself is biased. So even if we're being equally accurate, we'll be equally accurate in different proportions. So there's been a lot of work on fairness in machine learning, but it was a great starting point. But the problem with it is that any of these notions that are just based on using observational data are going to suffer these sorts of problems, because crucially they don't model how discrimination is happening within the data. So what we decided to do is propose a different approach that uses causality to model these unfair influences on these features. What we can do is we can construct the causal graph that we think most directly describes our data, most accurately describes it, and we formulated a definition that says, well, a predictor is unfair if it gives you a different prediction if, based on the causal model, we can imagine what your features would be if you had had a different race or a different gender. We can ask these kind of questions with the causal model. Another nice thing about our method is that the notion of counterfactuals is frequently used in places that debate things like fairness, like ethics and law, because this is a very interdisciplinary topic. So we looked at this for our data set of law students from the US. And what we're able to do is say, okay, fit this causal model that we believe best represents our data, and then imagine sampling people that are exactly the same except, for instance, their race had changed or their gender had changed. And if we use the predictors where we use all of the features, or maybe all but the sensitive attributes, we get vastly different predictions. So this is the danger. And another thing that our method allows us to do is, let's say we have a different causal model for a New York City stop and frisk data set. what we can do is we can look at the arrest rate for New York City. This is in 2014, where white is not arrested, red is yes arrested. And we can imagine what happens if everyone had been a different race. How would that have changed the arrest rate according to our causal model? So this will all change. I'm focusing on this particular area up here, but you can look anyway. So let's imagine that everyone had been white. What would have happened according to our causal model? Well, what you can see is that a lot less arrests would have happened according to our model. Or if, let's imagine everyone had been black, more arrests would have happened, or another race in our data set called Black Hispanic, even more arrests are happened. So our model allows us to sort of tease apart these mechanisms. So I'd like to thank my co-authors, Chris, Josh, and Ricardo, all at the Allen Institute. Thanks for listening.